Welcome to the Explainer CS students. All right, let's just get right into it. If you're studying computer science, you've definitely heard the two words that just strike fear into the hearts of coders everywhere: dynamic programming. It has this awful reputation for being this terrifying, insanely daunting paradigm that's just there to ruin your whiteboard interviews. But today, we're going to completely flip that script. We're going to demystify dynamic programming together, strip away all that intimidation, and see exactly how and why it actually works. Here is our game plan. First, we'll look at the core problem with standard recursion. Second, we'll introduce the dynamic programming antidote. Third, we'll break down the 4 pillars of DP. And finally, we'll apply all of this to a real-world scenario with word segmentation.
Okay, Part 1. The problem with recursion. To understand why dynamic programming even exists in the first place, we have to look at our old friend standard recursion. We know that massive problems can usually be broken down into smaller, bite-sized subproblems, right? And we typically use recursion to tackle those tiny pieces. But there is a massive hidden trap here. When you break a main problem into subproblem A and subproblem B, and then follow those branches all the way down the execution tree, you eventually hit a wall. You'll often find a node that has literally been solved before. Subproblem B might be generated and solved all over again on a totally different branch. Standard recursion has absolutely zero memory. It doesn't remember doing the work, so it just blindly does it again.
And that amnesia makes standard recursion unnecessarily expensive. In computer science, computation is an economy. CPU cycles take time, and time is expensive. When your algorithm is stuck solving the exact same subproblem over and over, it's just burning resources. If you throw a massive data set at an algorithm like that, those redundant calculations will literally bring your program to a grinding halt. We need a better way.
Which brings us to Part 2, the dynamic programming antidote.
DP is not here to punish you, I promise. It's actually the exact efficiency tool you've been looking for. When we compare the two, standard recursion is wildly expensive because it constantly solves the same subproblems. But dynamic programming, it is incredibly efficient. Why? Because it literally just saves its work. It stores the solutions to those subproblems so it can just reuse them later. It is a total game changer for managing computation.
Think of dynamic programming as the ultimate antidote to that recursive trap. It's a technique that just hoards solutions in a memory bank. By keeping a record of past answers, DP guarantees, absolutely guarantees, that each unique subproblem is solved at most one time. Just once. When your program stumbles into that same subproblem again, it skips the math, looks up the answer in its memory bank, and instantly moves on. This one simple trick takes algorithms from utterly unusable to lightning fast.
So let's get into the mechanics in Part 3, the 4 pillars of DP.
DP isn't magic. It's a methodology, and it is completely rooted in 4 specific academic terms that you really need to lock down. We can mentally organize these into 2 buckets. First are the essential attributes, meaning the characteristics a problem absolutely must have to be a DP candidate. That's your optimal substructure and overlapping subproblems. Then you have the essential components, the actual ingredients you have to write into your code. Those are the recurrence relation and the base cases. Let's walk through exactly what these mean.
First up is optimal substructure. This basically just means that the absolute best optimal solution to your giant problem can be perfectly constructed by combining the optimal solutions of its smaller pieces. If a problem behaves like that, it's basically raising its hand saying, hey, I'm a perfect candidate to be broken down.
The second essential attribute is overlapping subproblems. Remember that solved before trap we talked about earlier? That's exactly what this is. It's when the exact same subproblems pop up repeatedly during your process. Look, if every single breakdown creates a completely brand new, unique question, DP actually won't help you at all because there's nothing to reuse. But if those subproblems overlap, oh man, DP is going to be your best friend.
All right, let's pivot to the code side. The third pillar is a recurrence relation. This is the mathematical backbone of the whole operation. It is a formula that explicitly defines the solution to the big problem using the solutions to its subproblems. This is where you write the logic telling the computer to get the answer for n, do this specific math using the answers from n-1 and n-2. It's your blueprint.
And finally, the 4th pillar, base cases. These are the absolute simplest, most bare-bones instances of the problem where you already know the answer. No more decomposing required. If the recurrence relation is the blueprint, the base case is the solid concrete floor. Without them, your recursive loops would just fall forever into an infinite abyss. Base cases are the crucial stopping point that allows your algorithm to finally start bubbling all those stored answers back up the chain.
Let's see this in action in Part 4, Real-World Word Segmentation. I want to get out of the theory for a second to prove this isn't just arbitrary whiteboard trivia. Think about search engines. You ever type really fast, totally miss the spacebar, and just mash a bunch of words together? The search engine still magically knows what you meant. It does this through a process called word segmentation, and search engines rely incredibly heavily on dynamic programming to pull it off. When you give it a block of text without spaces, DP jumps in to figure out exactly where spaces can be added to form a valid sequence of dictionary words.
Let's actually trace how that algorithm works. Step 1. You type the original mashed-up query, best restaurants. Step 2. The algorithm has to test all the possible ways to insert spaces. It might check best restants, solving for each little text segment just to see if it forms a real word. It is testing thousands of distinct paths here. Finally, in Step 3, it zeroes in on the optimal valid string, best restaurants.
And DP is the absolute MVP of this process. The algorithm solves each segment separately, but critically, it stores those solutions. Once it figures out that rest is a valid word, or that R is absolute gibberish, it saves that fact into its memory bank. It actively avoids recalculating those exact same text chunks as it continues to test different space insertions. Without DP storing those answers, checking every single combination in a long search query would be computationally impossible. With DP, it's practically instant.
So, we have seen the trap of redundant recursion, we've mastered the 4 pillars, and we've seen DP flawlessly segment complex strings in the real world. Which leaves me with one final question for you to ponder as you look back at your own code bases. What unnecessarily expensive recursive loops are hiding in your projects right now, solving the same things over and over again, just waiting for the dynamic programming antidote? Find them, apply these 4 pillars, and watch your algorithms absolutely soar. Thanks for tuning into this explainer, and happy coding.